Hello everyone, my name is Francisco Borja Saavedra, and I'm a third-year industrial PhD student at ENI Space, and I'm here to talk about the sizing and direct characterization of externally wetted ionic liquid electrospray thrusters. So I'll start with the problem motivation. I'll go through this a bit faster because this is not the first time. But basically, the motivation is relatively simple. There has been an industrial growth in the small satellite market in the last few years, as you can see in this graph. But if you look at the curve of those that carry onboard propulsion, is really dragging behind. So the main motivation is this lack of propulsion adoption in the very small platforms. The reasons behind this are several, mainly the strict constraints and the great platform variability of these nanosatellites mostly. But we've also seen that there's this lack of dedicated knowledge, let's say, to kind of like couple propulsion and the orbital dynamics to make like a cohesive design in a way. Regarding the propulsion itself, it's clear that chemical propulsion can't deal with these platforms many times because mostly of mass and volume restrictions. And on the other hand, like plasma electric propulsion systems are difficult to miniaturize, and the power limits that are usually 1 to 2 watts per kilogram are too restrictive, let's say, for the smallest platforms. So this kind of like justifies the recent increase in interest in other technologies like FEEP or electrospray, which is what I'm talking about here, because basically it promises high efficiency at low powers. Just a bit of introduction of the electrospray technology. The concept basically consists in the extraction and acceleration of ions from an ionic liquid by imposing an electric field. And the advantages are that by using an ionic liquid propellant, you don't need any pressurization. It is stable in vacuum, and mostly it permits emission of both polarities. So under good conditions, it wouldn't require a cathode. And the pure electrostatic emission, as I said, the main advantage is that it's low power and it promises high efficiency. As there's no plasma, there are no other like big losses. But again, if you do everything properly. So regarding the objectives of this work, it is very aligned with the development of the electrospray thrusters at ENI Space, and we do this in a concurrent way with mission analysis. So the first objective was to develop a preliminary concurrent design tool for, as I said, preliminary mission analysis for scalable electric propulsion systems based on electrospray. Then to develop a direct performance measurement system for these thrusters to actually measure the performance, and then to iterate with the tools of software and hardware to find like next generation thrusters. Basically, as I said, we're in a development phase. And finally, well, there's a fourth objective that is to provide some insight into the effects of electrospray on spacecraft charging, and hopefully being able to simulate or even to measure, like characterize it experimentally. I'll go now to the methodology and results for each of these objectives. So regarding the preliminary design tool, we have developed this tool called Go as part of my thesis that basically tries to solve the inverse problem. So the idea is that you take as input the platform data, the maneuvers you want to do, and with a scalable propulsion model, as I said, based on electrospray, the idea is that the output of the tool is the main performance parameters of the thruster. So you're optimizing the thruster as a result, let's say, and not taking a thruster as input and then optimizing the maneuvers. Basically, Go is based on simplified dynamics using the orbital averaging technique and includes low thrust, the J2 and the drag circular perturbations. It's single objective, multiple constraint optimization with some predefined near optimal trajectories. It has been benchmarked against GMAT. This figure shows just an increase in inclination, just as an example, and is available publicly. So then moving on to the more experimental part of the direct performance measurement system. Basically, this is the main challenge, let's say, of the thesis, because it requires measuring repeatably and accurately thrust of the order of micronewton and mass flow rates of the order of milligrams per hour. So it's really sensitive, let's say. Torsional balances are like the common practice, let's say, in the thrust and literature for these ranges, but they require costly optical sensors. And for the mass flow rate measurements, you typically need an additional diagnostics, although there's an instance of a dual axis thrust mass torsional balance, but it's much more expensive and complex. So the idea in this thesis was to go for vertical balances that have also been tested actually in the literature for electrospray thrusters. And they're more cost effective, and under the right conditions, you could also measure, as I said, the mass flow rate. So what I did basically was to take a high precision analytical balance, kind of like dismounted and adapted for vacuum, that has a readability of 1 micronewton and a maximum load of about half a kilo. Well, and it's based on electromagnetic force restoration. So basically, the main perturbations that affect the measurements in these ranges are, well, first you have air buoyancy, but this goes away during the pump down, of course, in vacuum conditions. You have other mechanical perturbations, electrostatic, if you may have differential charging, so all these things you have to take into account, let's say. The main issue is you need actual physical electrical connections for the thruster. So again, it's common practice in the literature to use liquid connectors using some liquid metal like Galveston. And I have tried them, but this introduces also other issues like the buoyancy. The metal can creep up the electrodes. Basically, it produces outgassing that is manifested as those bumps you can see in this curve. That is basically the behavior of the balance during a pump down, and other interactions. And of course, if you feed like high voltage that is needed for our thrusters through the liquid connectors, you're going to have some electrostatic interaction directly on the axis of the balance. So this was kind of problematic. So the other solution that was tried is just to use wires, physical wires, but using single filaments. So the smallest you can be, they're about like 60 microns in diameter. And this way it was possible to obtain like repeatable results, in principle without major perturbations, let's say, as you can see here. And these results were actually presented at IBC 2022 because they, to the best of our knowledge, were like the first thrust measurements of an externally wetted ionic liquid electrospray. But of course, as I said, the idea is to measure performance as a whole and not just the thrust. So for that, as I said, it's milligrams per hour, which is roughly some micronewton per hour perturbations that you need to control. So that's pretty challenging. So more efforts were made into, let's say, the calibration and stability of the balance. So regarding the calibration, first a set of high accuracy, high precision calibration weights was acquired to actually, let's say, calibrate the balance, because as I said, it was adapted to vacuum. This is an analytical balance that was not meant for this. So we use these calibration weights to kind of see like real against measured force, basically, and the results are shown here. As you can see, it agrees very, very well, considering also the air buoyancy and the local gravity, because even that affects the measurements, the gravity constant that you use. So we use this curve to basically, well, I developed this electrostatic calibration device, not to do the calibration process with the weights every time, because it's quite time consuming, of course. And it's actually based on electrostatic comps, but built using heat sinks, commercial off-the-shelf heat sinks. And I use the calibration data from the calibration weights, basically that curve, to characterize the force that this device produces against the voltage, so that this is kind of like the calibration device used for next tests. On the other hand, regarding stability, I performed several pump down tests of several days long, because as I said, you need to really be aware of the different perturbations that affect the balance. As you can see that the force kind of follows the temperature, the slope of the temperature. The correlation is still like being investigated. But what you see is basically very low frequency oscillations, but without the liquid connectors, I didn't see any bumps or weird perturbations, let's say. And it kind of follows 24 hours thermal cycles. So the best approach is to, as is typically found in the literature, because mass measurement, direct mass, like in situ mass measurement is not as common for these ranges. The best thing to do is basically to take this background drift and kind of like subtract it from your measurements. So basically with this, it was possible to measure the mass flow rate in a first time, let's say, for these externally wetted ionic liquid electrospray thrusters. I did this test at different emitter voltages, and these are the results. I'm not doing a plot because, as you can see, at the first voltage that I tested, the thrust was so low that was below the resolution of the balance. So it's a plot of just 2 points is kind of, well, not enough, clearly. But this is basically the last milestone regarding this experimental activity, and the next steps will, of course, be to test in this way to characterize the full performance of the next of more thrusters, and of course to do it in more at more points and so on. So regarding the other objectives, the sizing, the third objective is the sizing and characterization of the next generation thrusters is now possible to do, of course, because we can now like actually measure mass flow rate and thrust so to obtain the total performance. So this will be, this is kind of already happening, but it's going to happen soon. So this is the very next step. And finally, regarding the last objective, that, as I said, it's not really the main one. But this, we have developed a preliminary charge sensor setup to actually measure the charging of a floating system based on electrospray in a vacuum chamber. And well, there has been some simulations about the charging in the space environment. As I say, it's not the main objective, but well, it's there. So there's already some progress into that. Anyway, just to finish, I don't know if I was too quick. Basically, these are the publications and other activities that I've done until now. Mostly, as I said, the IAPC 2022 last year, presenting the thrust measurements and so on. The mass flow rate measurements are early, let's say, to present them. Well, as you can see, those are conference papers, and I have done other activities and others I'm not listing here. But of course, I still have to do my journal paper. But since it's kind of like depending on the manufacturing of these next generation thrusters that I said, so it's kind of like it's depending on that. So, but it will start really soon, actually, really soon. So yeah, that is all. And thank you very much for your attention.